Okay, so this is lecture 5 of Algebra and Computation. So I actually do not know, I don't have a good sense of how long today's lecture is going to be, because a large part of it is going to be trying to find a solution to the Rubik's Cube on our own. So on Academy, there were a bunch of questions that were asked, but I guess people, I mean, besides Varun, haven't tried out, but I hope that you have tried out at some point. If not, maybe during the class or something, you can still think about other ways of solving the same problem, because there's not just one solution, there are plenty of solutions. Okay, so today, what we are going to do is, I'll tell you about two concepts which are called conjugates and commutators. Both of them in itself is actually very simple. I mean, these are things that you likely have seen in other contexts also, and but it's just that these two alone, in my opinion, are more or less enough to basically solve most permutation puzzles. Okay, but again, I just want to stress that when I mean you can solve these permutation puzzles, this is nowhere going to be close to the best way to solve these puzzles. Okay, like for example, if you're interested in doing it in the least number of moves or the fastest or something, obviously this is not what you should be doing. There are better ways of doing that, but even if you're interested in, let's say, something like speed solving or whatever, I mean, knowing commutators is very useful. In fact, what I'm going to hope to teach you today is not really to solve the cube, but rather to teach yourself to solve the cube. In fact, the method that we are going to be using is what is often used for blindfold solves. And we will see exactly where it shows up and so on. And it's actually not as hard as one might think it is. I honestly think that if you have the ability to memorize a sequence of 20 letters, I believe you should have the ability to solve the cube blind. But anyway, we'll see. Okay. So just a quick recap, though most of it will not be really relevant for today's talk, which is that so far we have seen a whole bunch of algorithms for various basic tasks involving these permutation groups. Okay, and somehow the setup we always had in mind was the Rubik's Cube or something, because there's a certain set of stickers or whatever we had, and there are these groups that seem to be acting on these stickers. Okay, and so that was roughly what we were thinking about. And we did things like, we got a sense of what orbits mean, what orbit representatives mean. And then we did algorithms for each of these things, along with membership testing, finding a size of a group, checking whether something is a subgroup or not, checking whether something is a normal subgroup or not, etc., etc. Okay, so today we won't really be dealing too much into those, whereas, I mean, they'll just keep coming in passing. But I'm going to just focus on these two, conjugates and commutators, and just tell you how it will be, how it can be used for a variety of, for just coming up with systematic solutions to a variety of these permutation problems. Okay, so let's begin with conjugates. This is probably something that you have seen in plenty of other contexts. I mean, in some sense, I mean, very vaguely speaking, these are basically what I call basis change. Okay, because I mean, these sort of operations are things that you might have encountered in, say, linear algebra, where you have a matrix G, instead of G, there'll be some matrix, I don't know, B or something, and you will have some change of basis matrix A, and you might often look at A inverse B A, or sometimes it's like A B A inverse. I mean, it's just a question of notation, but this is what we would say. I don't know why this was in H. This is a conjugate of G with respect to sigma. Okay, so that's what this conjugate means. I will also add one warning that in some places, unfortunately, this is also referred to, the sigma inverse G sigma is referred to as G power sigma. And obviously, I mean, at this point, since we are using this exponent notation for a whole bunch of things, this is going to annoy us a lot. So I will not use this notation because I want to leave the exponent notation for a group action. But if you're reading some notes and it shows up, you know what that means. So the first thing we are going to try and understand is, what do these conjugates do? Like if G and sigma were two specific permutations, what does the conjugate look like? Okay, so let's just try out a couple of examples so that we hope to notice a certain pattern, and then we'll try to prove that that is indeed what is happening. So, okay, so it's often easier to write this in the array notation. I mean, whenever we are trying to figure out what happens under a product, it's often easier to do this. So let's see, where does 1 go? So sigma inverse will map 1 to 5 because it's mapping 5 to 1. So sigma inverse will map 1 to 5. And here 5 goes back to, 5 goes to 1. And then again, sigma maps 1 to 2. So here 1 is going to go to 2. I hope that's okay. I mean, okay, now let's look at what is the image of 2 going to be. Sigma inverse is going to map 2 to 1. And then 1 goes to 3. And then 3 goes to 4. So this is going to be 4. Can someone tell me what is the image of 3?
4. 3 goes to 2.
3 goes to 2 here.
And 2 goes to
2 goes to 4.
And then again
4 goes to 5. So this should be 5. And 4 is going to be, 4 goes to 3. 3 goes to 5. And 5 goes to 1. So therefore 4 goes to 1. And therefore this is supposed to be 3. Okay. So if we write this in cycle notation, 1 is going to 2. 2 is going to 4, and 4 is going back to 1. And then 3 is going to 5, and 5 is going to 3. That's just a different way of writing the same thing. Okay. Now let's try one more example where we'll just use the same sigma, and maybe let H be equal to this pair of transpositions. Okay. Then again, let's write 1, 2, 3, 4, and 5. So let's get a sense of where is 1 going to go to. So here, again, 1 goes to 5. 5 doesn't move at all here. And then 5 goes back to 1. So therefore, 1 stays at 1. Okay, and what about 2? 2 goes to 1. 1 goes to 3, and 3 goes to 4. So here 2 is going to 4. And I'll just fill this up. So, I mean, like you can check this if you want, but this is the answer that you end up getting. So again, let's write this in cycle notation. 1 is just staying where it is, so we don't need to bother about it. And then 2 goes to 4, and then 4 goes back to 2. And then 3 goes to 5, and 5 goes back to 3. Okay. So one thing that seems to be happening is that somehow the structure of this and the structure of this seem to be the same. Okay, and similarly, the structure of this and the structure of this seems to be the same. So I mean, one might say that, maybe it's a consequence of what the sigma looks like. But you can try out more, but maybe at this point you start wondering. Whereas, is it the case that somehow this quantity is somehow similar to G in some sense? And now you probably see where the word similarity comes from, because at some point you want to say that they have a very...
So conjugates, by conjugating, it preserves somehow the cycle structure.
That's right. So that's what I want to, that's a conjecture I want to make. And in fact, the answer is, it is indeed the case. And in fact, it's something even stronger than that. So let me write this a little differently. This cycle permutation is the same thing as writing 2, 4, 1, and I'm going to write this as 3, 5. And this I'm going to write this as, this let it be 2, 4, and okay, this is also 2, 4, 3, 5 is already okay. So the point is, okay, what this observation is basically saying is it's telling you precisely what the conjugate is going to look like. Okay, notice that this is 1, 2, 4, and 3, 5. Now just imagine sigma as being some sort of a relabeling operation. Okay, so then 1 is getting relabeled by 2. Sorry, did I mess something up here? Sorry, this was 1, 3, and 5 here. So 1 got relabeled by 2, and 3 got relabeled by whatever this was, 4, and 5 got relabeled by whatever this was, which was 1. So we're literally taking the cycle representation we had for G and just applying sigma in every index in some sense. So I hope that makes sense. So G was originally 1, 3, 5. Just imagine relabeling all of these 5 characters you see using sigma, but otherwise keep the cycle structure as is. Then what you end up getting is 2, 4, 1, and 3, 5, which is what the conjugate was. So similarly, if you look at 1, 3, and 2, 4 and apply this whatever relabeling operation, so 1 will go to 2, 3 will go to 4. So 1, 3 becomes 2, 4, and 2 goes to 3, and 4 goes to 5. So 2, 4 became 3, 5. So it's a literal relabeling operation, and that's what this observation basically says. It says if G has this particular cycle structure, that is, I'm just writing it as A1 to AK1 ... B1 through BK1. I mean, I don't know how else to write this nicely, but you sort of understand what this means. And then the conjugate is basically you literally just relabeling every coordinate. Okay. So an obvious consequence is that, of course, the cycle structure is present. I mean, the above observation is saying a lot more than just saying a cycle structure is preserved. It's telling you precisely what the cycle structure is going to. I mean, precisely what the cycles are going to. Okay. So just here is just a one-line proof of that. I mean, what do we need to show? Okay, maybe I'll just do this completely. So what do I need to show? I want to basically say, okay, what I want to show is the following. So suppose I power G is equal to J. Okay, then I want to know what does this do on I power sigma? That is, or what does it do on sigma of I? Okay, so then, so let's take sigma of I and apply the conjugate on it, which is sigma inverse G sigma. So what is this going to be? So the sigma inverse will move sigma of I back to I first. Okay, so this is I power G sigma. Now we know I gets moved to J. So this is J power sigma, and J power sigma by definition is sigma of J. So what this says is whenever your old permutation was moving I to J, your new permutation is now going to move sigma of I to sigma of J. Just put that together and you get this, basically. Okay, so was this fine? So this basically is why conjugates in some sense are like a basis change, because you are saying, look, I know what G does, but G has its own mental picture of what the stickers are labeled as. But suppose you want to do basically the same operation, but your labeling is different. Then to fix it, you will apply a conjugate. Okay, so that's what conjugates are meant to do. Okay, and once we have defined conjugates, there is a notion of what is called a normal closure of a subgroup. Okay, which is basically, it's the smallest subgroup that contains the elements of H and all its conjugates. Okay, or in other words, what does it mean for a group to be normal? The group to be normal was saying that whenever G, or rather, normal meant that if H was in H, then GH, G inverse or G inverse H, this was also in H. So in some sense, what it's saying is that if an element is present there, then all its conjugates are also present there. That's what it means to say that something is normal in something else. It's like, I come with all the people I'm similar to. Okay. So a normal closure is basically what the words seem to imply. You just start with your subgroup and close it under this normality relation. You're basically asking, okay, if I want to make H a normal subgroup, I may be forced to add a few more elements to it because I have to add their conjugates. What's the smallest number of elements I need, or what the smallest set of elements I need to add to all of this so that you now end up with a normal subgroup? That's called a normal closure.
Why? I mean, I've always wanted to know, why is this called normal?
don't have a good answer except that.
Does it have anything to do? I mean, normal in the sense of perpendicular. I can't think of anything.
It's just that, I mean, all other situations where something similar happens, the words are all rather epic, right? I mean, like, for example, in rings, the version of a normal subgroup is an ideal. Like, what's so ideal about an ideal? I mean, so I don't have a good answer to this.
Oh, right.
Yeah. So, but so technically speaking, in my opinion, normal probably means it's like kernel-like. It's things that behave like a kernel. Okay, and it's in fact there is more truth to what I'm saying. In fact, all of these are kernels. But okay. Okay. So now one can ask this as a task now. I give you a group H as a generating set, which is a subgroup of a group G. Now I want you to find the normal closure of H in G. Again, by find, what I mean is I want you to find a generating set. Okay. Can someone outline what algorithm you will want to do at this point? I mean, like, what would you want to do?
Can you repeat the question?
So I give you a generating set T, which happens to be a subgroup of some other generating set S. Right? So S and T are what is given to you as input. And what I expect from you is to compute a generating set for the normal closure. That is the smallest normal subgroup that contains H. I mean, inside G. Was the question clear?
Didn't we see this at the end of the previous class? Like, basically, I mean, the normal closure tells us that, okay, you want for every H in capital H, you also want G.
So last time we were just testing normality. We were just testing whether this subgroup is a normal subgroup of this. But you're right.
Oh,
so
but I mean, just include each of those.
Right. Yeah. When we answered no, we said because there is some element you ought to have added, but you didn't add.
You didn't. So you just add.
Okay, so let's add that. The only thing is you might have to do this repeated number of times because you've added some new elements, which means there are some new conjugates possible. So maybe you'll have to do this. So I'm just writing down.
Basically, we just take intersection over sigma H sigma prime.
No, how do you take an intersection? I mean,
means I'm saying that we are taking elements minus G minus H, taking any sigma from G minus H.
So by the way, we don't have access to G or H. We only have access to S and T.
Yeah, S and T. I'm saying just
okay.
I'm saying we will first do the means over the element of the taking any elements from S. I will do the conjugation operation using the elements of S over T. And I will take the intersection then.
No, intersection with what? Can you be more precise?
Over the means for each element of S. For each.
So let's say you pick up an H here, you pick up a G here. Now you look at G inverse HG.
Yes.
What do you do then?
No, firstly I pick up a G here from G. Okay.
Okay.
So I am trying to compute G inverse HG.
H is also an element of T or?
For all H.
For all H where?
In H, capital H.
No, but I can't do that, right? This H could be a huge subgroup.
Only we'll do in generators only.
Okay, so that's what I'm saying. So suppose you pick up some H in T and some G in S.
Yes.
And now I compute the element G inverse HG. What do you do then?
Yeah, and I will compute for all H, for all generators in T.
No. Right now you have one element. What do you propose to do with this one element?
So I will take it count for all H.
Again, take a count of what?
Means I will give a set. I am trying to create a normal subgroup, right? Which contains firstly contains H.
Okay.
So what is to be proposed that firstly under obviously that that if the subgroup is K, then K inverse sigma K sigma inverse K sigma is already subset of K, right? That automatic implies that sigma inverse H sigma subset of K.
Okay.
Right?
Okay.
what I'm trying to do, I'm trying to gather all such elements that is of the form G inverse HG.
Okay.
And then I'm trying to see it is closed and it's preserved the group operation.
So the thing that at least to me, it's like, maybe it is true, but it's not clear to me is the following. Let's say we start with a T.
Yes.
And we notice that G inverse HG is not present inside this subgroup H.
Yeah.
This we can check by a membership test.
Yeah, yeah.
Right?
We will add it to.
So we'll add it. But the point is, now I've added a new element. Maybe there are new conjugates that I have not found yet. Right? So it's like not clear if I can do this just once.
No, just
stop there.
I have to do it till I just said we have to vary the G over S.
No, that I understand, but I'm just saying that, so this algorithm does a slightly different thing, which is what it does is, in one shot, it basically says what are all new elements I need to add to my set. So it adds all those elements to that set. Okay. Now it tries that again. With now the set T has expanded to a slightly larger set, but now it runs the same algorithm with this new thing. So either your group grows or your group is already sort of stable under this operation.
Yes.
If it is stable under the operation, that is the B did not change, then you just return B. You exit this loop and return B. But if B does change, then you keep repeating it. And like we did last time, the number of times B can keep increasing is only going to be something like N of them, because the group size doubles at everything. So this is one algorithm that at least to me seemed like non-controversial. Like it's very clear that this algorithm should work. Okay. Okay, good. So just to maybe make sure that we understand what normal closure means, here is a simple question. Suppose your group G is the set of all possible permutations. And H is basically the group that is made up of two elements, the identity element and the transposition. That's it. So it's the group generated by just one transposition. What should the normal closure be?
Oh, so wait. In the normal closure of H in G. So
normal closure of H in G.
So I mean, not thinking about this procedure and just thinking that you want all relabelings.
Yeah, exactly.
To be
don't worry about this algorithm. Just
Then all transpositions.
Right. So whatever is this group K, one thing here are some things that this group K must definitely contain. Well, if it contains this one transposition, it is supposed to contain all the things that are similar to it, which in particular mean it contains all transpositions. So if you know that you have a subgroup that contains all the transpositions, well, that group will certainly generate all of S.
All of it.
Right. So the normal closure of H inside G is actually equal to G itself in this case. I mean, once you close it, you basically get the whole group, even though to begin with, this H was tiny, like there's barely anything in it. Okay, but everything goes inside. Okay, so much for normal subgroups and normal closures and so on. He doesn't hold on to the thought of conjugates because those will make its appearance soon. Okay, and then there is this notion of what are called commutators. Okay, these are basically operations of the form do something else, undo the first thing, undo the second thing. Okay, these are expressions that look like GH, G inverse, H inverse. Okay, turns out this is also an extremely important thing to study, that there is something called a commutator subgroup. Okay, which is basically you collect all possible commutators and put them together and look at the group generated by them. That's what the commutator subgroup is defined as. Okay, I won't be going into too much details about it, even though this is an extremely important thing that people study, just because it's not something that we're going to directly use in our course. But if you're interested in more stuff, we'll do it. I mean, you can look at the notes from the 2017 offering or something. Okay, but one fact that maybe I'll tell you at this point is that this group, the commutator subgroup, turns out to be a normal subgroup of G. Okay. From the definition, it's not readily apparent why this is the case, but turns out it is a normal subgroup of G. Okay. And again, you can ask this task of, I give you a set S, I mean, I give you a group G via a generating set. And I ask you, can you compute the generating set for the commutator subgroup? Okay, any guesses on what this algorithm should be? There's one obvious thing that
By
you can
definition,
do.
it is clear, it is normal.
Sorry?
By definition, it is clear, it is normal.
Oh, is it?
You have just to change the inverse operation.
Sorry, what do you mean by change the inverse operation?
So normality means that you are doing G, means you are looking at H inverse any element from G comma G, H.
So you're looking at, let's say, I don't know, H inverse.
AB, A inverse, B inverse. H.
Okay.
H.
Oh, I see. You write this as H inverse AH and then H inverse BH. And then, oh, okay. So you just put an H inverse H in the middle of each of the four things.
Yes.
Okay. Yeah, that it is normal is clear. That's right. Okay, great. So there's this thing. So one natural sort of knee-jerk reaction to constructing a generating set for this is you just take all elements of the form A, B, A inverse, B inverse, where A is an element of S. Obviously, these must be things that you should take. And one can hope that this actually generates the entire commutator subgroup. But turns out it actually doesn't. There are examples where this doesn't. But what you can do is you can do the normal closure. The normal closure of this with respect to S, and that turns out to be a generating set for G. If you want to see precisely why, I will let you look at the notes from 2017. But at least just want to tell you that there are algorithms to do this. You've already seen a normal closure algorithm, and you just need to do the obvious thing, but don't just output that, output the closure of that. And that works. Okay. And now comes to the part where I think is perhaps the most fun thing of these sort of commutators. Why commutators are so interesting. What I want to do is the following. Suppose I have two different permutations G and H. I want to know, what do these commutators look like? What do they end up doing? Okay. Okay. So let's just write down what is this commutator supposed to do. So it's 1, 2, 3, 4, 5, 6, and 7. Okay. Where is 1 going to go by this operation? So 1 goes to 2. This doesn't do anything to 2. And then when a G inverse moves back to 1, and again this inverse doesn't do anything to 1. So 1 stays at 1. Similarly, 2 stays at 2 because 2 goes to 3, H doesn't do anything, and then it eventually comes back. Okay. What happens to 3? 3 goes to 4. That 4 gets pushed to 5. And then G inverse doesn't do anything to 5, but then H inverse will push 5 back to 4. Is that okay? So this, you end up getting 4. I mean, I maybe went a little faster, but I hope that was okay. So now let's look at what is the image of 4 going to be. 4 goes to 1, okay, due to G. H doesn't do anything to 1. And G inverse will move 1 back to 4. And this moves 4 to 5. Did I make a mistake? Oh, sorry. There's an H inverse, so it goes to 7. So let's just go over this again. G moves 4 to 1. H does not change 1 at all. And G inverse moves 1 back to 4. And H inverse moves 4 back to 7. Because, okay, so that goes to 7. Again, let me just write down what this is. You end up getting 5, 6, and 3. Was there a question?
No, actually, I just told that you previously did a lemma, right? How G inverse H G will look like. Just do that and then conjugate H inverse. That will be very easy computation.
Oh yeah, so we can do that. So okay, so let me just write down what is this supposed to be. This goes, this 3 goes to 4, 4 goes to 7, and 7 goes back to 3. That's what this looks like. Okay. Now the point is, instead of 1, 2, 3, and 4, had we taken something like 1, 2, 3, blah 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 till 50, that was my G. And my H was equal to 50, 51, blah, 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 till 100. Okay. And we did exactly this G, H, G inverse, H inverse. What are the things that would end up moving? So what will the image of 1 be? Because 1 gets moved to 2, this guy will do nothing to 2. And 2 gets moved back to 1. So really what's going to happen is only like some very locally around this intersection. Okay, so it seems like a very local operation. In fact, I will let you check that this is in fact going to just be 49 goes to 50, 50 goes to 100, and 100 goes back to 49. Okay, I'll let you verify that if you compute G, H, G inverse, H inverse, that's what you will end up getting. Okay, and so let's in general define this notion of what is called, suppose you have some permutation G. Let's just say move of G is the set of all elements that are moved by G. Okay, so it's just some notation that I'm choosing. And this is a lemma which in my opinion is just super, super powerful. If you haven't seen this before, it's like a very eye-opening sort of lemma. It is the following. Suppose my sigma is the commutator. By the way, this is just the notation for G, H, G inverse, H inverse. It's just some shorthand. Okay. Let's define the set S to be the common elements moved by both G and H. That is, it's just the intersection of move G and move H. Okay. Then if you ask, what are all the elements moved by sigma? They fall in these 3 categories. Either it's one of these common elements, or it is something where, so this is basically the set of all I such that I power G is an element of S. That is the things that G moves to this common set. And these are things where the set of all I such that I power H falls inside this common set. So in other words, the only thing that the commutator moves are either those that are common elements or the pre-image of this common elements under G or the pre-image of the common elements under H. Okay, so I hope the statement of this lemma is clear. We will just see a short proof. The proof is really, really simple. It's just some case analysis. Okay, but is the statement okay? So in the previous situation, what are the elements moved by G? It's 1, 2, 3, and 4. And what are the elements moved by H, which is 4, 5, 6, and 7? This common set is just this set 4. It's a singleton set 4. And what's the pre-image of this set under G? It is just 3, because 3 is the thing that got moved to 4. And what's the pre-image of this set under H? It's 7. So the only 3 elements that can move are 3, 4, and 7. And that's also why the same argument, the common set was just 50. And the pre-image under G was 49, the pre-image under H is like 100. Okay, so it's not that these are cycles that it was important. What seems to be more important is the fact that they together move only one common element. Okay, so let's see a proof of this so that we have hopefully have a better appreciation of this. So we need to do a bunch of case analysis. I want to basically take an element I that is not present on the right hand side and show that it is not moved by the commutator. Right. So let's pick a okay. Say some element I is not in the RHS. Okay. So with me, which in particular means that it is not present in the intersection. That is it. Okay. So let's say case 1. Okay, I is not in move G and I is not in move H. That is, I is an element that's not moved by G, that's not moved by H. So why the hell will the commutator move it? None of them are moving it anyway. So this is just, I mean, it's like trivial. Okay. Now the interesting case is when this other thing happens. So case 2, let's say I happens to be in move G, which means that I should not have been in move H. Right? Because otherwise it will end up falling inside S. Okay. And so what else can we say in addition to this? So what can I say about I power G? I claim this should also not be in move H. Can someone say why?
I mean, because I is not in RHS, which means...
Yeah, so if I is not in RHS, which in particular means that it's not in this set. Or so rather, it's not in this set.
Yeah.
Right? Which means if I power G happens to be in move H, then whatever that image was, that happens to be here. And we said that's not possible. So therefore, this is what we know from the fact that I is not in the RHS. If I know I is moved by G, then I know I is not moved by H, and the image of I is also not moved by H. Those are two facts that I know. Okay.
Wait, so there's some one extra step here, or I mean, this at least the I not being in RHS tells us that I to the power G is not in move G intersection move H.
Mm-hmm. So okay, so let's just say this I power G is equal to J. Right? Now J is certainly in move G, because if I move something to J, I mean J must also be moved by G.
Sure. Okay.
So then J will end up being something in the common thing, which means that whatever.
If it's not here, then it should not be in move H. Yeah.
Okay, so this is what we end up getting. So then what does this mean? Now let's just write this down. So what is I power G H G inverse H inverse? So I power G was equal to J. So now I have J H G H inverse. But I know for a fact that J is also not moved by H. So therefore, this is just going to be, oh, I missed an inverse here. So there's going to be J power G inverse H inverse. And J power G inverse is I. So I have I power H inverse. And I know H does not move I. So therefore, this is equal to I. So far, so good. Okay, it's just some case analysis. You need to do exactly the same thing on the other side. That is, if I happens to be in move of H, then turns out that I can't be in move of G. And I power H is also not in move of G. And then you do something similar. Okay, I'll let you fill up the details. Okay. And it actually turns out that, if you just know commutators and conjugates, You basically can solve almost all permutation puzzles. Okay, and it's just because of this one corollary. Okay, suppose you came up with two moves G and H such that the set of common pieces was a singleton set. Then notice that the right hand side is a set of size at most 3, which means it can move at most 3 pieces. So what I'm saying is that if this S happens to be a singleton, this is a singleton, this is a singleton, this is a singleton. So certainly this union is at most 3 elements. So somehow you magically are able to come up with these moves that somehow locally only move 3 pieces. It doesn't change any of the other pieces. Okay, so is this corollary clear as to why this corollary is just a simple corollary of the previous fact? Now, why is it useful? The point is, often when you try and solve things like Rubik's cubes or whatever, you might end up with a situation where you solve everything except maybe one layer. And then you're looking to somehow make some local modifications without messing up the rest of the cube. So a large part of solving these permutation puzzles is like saying, can I do some, sorry?
Sorry to interrupt. Why not exactly at most?
So it may be the case that, some of these elements, even though it is in the common thing, like for example, here is a stupid example. If G was equal to H, no, that's not what I want. So suppose, let's say G was equal to H inverse.
Okay.
Okay, so then if the commutator looks like G inverse, G inverse, it doesn't move anything. So all we are saying is that if something is moved, it is present on the right hand side. But I'm not claiming that everything on the right hand side might be moved by sigma. Did that answer your question?
I didn't get the part actually, sorry.
No, that is if so, for example, think of the situation where you're looking at G inverse, whatever, G inverse G, which is literally the commutator of G and G inverse.
Yes.
What is move of this quantity?
There's nothing, exactly.
Nothing. So the left hand side is an empty set. But the right hand side is something, right? I mean, like, who knows? G could be some complicated thing that moves everything.
Okay.
So this need not be a tight, it's not always the case that this is an equality. There are situations where it's not an equality. Okay. So the point where this sort of thing turns out to be super useful is the following. Suppose you come up with some sequence of moves. Let's call that G. I ended up erasing it. Let's call that G, whose eventual action on the cube was the following. The top layer happened to be intact except for maybe this one corner. That one corner got knocked off. I don't care what happens in the bottom 2 layers. The bottom 2 layers can go to hell. Okay, we come up with any sequence of moves that knocks off one corner from the top layer, but nothing else. Now, similarly, suppose you come up with a different move, which only changes the top layer, but doesn't really do anything to the bottom 2 layers. Then, if you take the commutator of these 2 things, you will end up coming up with a sequence that moves 3 or fewer pieces. Okay, so this was one of the questions that we had asked on Academy. So hopefully you have your own sequences of doing this, and we'll just see a bunch of examples for this. So I hope the statement here is clear. I mean,
all you're saying is, so here G only moves this one corner piece, and H
so if I look at move of G consists of nonsense in the bottom 2 layers and this one corner.
Yeah.
Move of H consists of things in the top layer.
The intersection of both.
So the intersection is
one.
one piece. Okay, it's 3 stickers, but let's say one piece. Okay, and therefore, by the previous lemma, the commutator of G and H will move at most 3 pieces. Okay, so let's see this in action. So I'm going to stop. Maybe I'll just start sharing here. That should stop the other thing. I want to continue. What do we want to share? Yeah. So can someone, are people able to see this thing that has alg.cubing.net?
Yeah.
Okay. So let me just start off with, I'm hoping that people have tried this out. It's a nice app where you can just write down your moves and it just executes them. So for example, if I write R and D, okay. So what it ends up doing is like R refers to turn the right face clockwise. Sorry, let me just go here. Turn the right face clockwise, and D refers to turn the down face clockwise. If you want to turn things anti-clockwise, you put a prime. So that's so for example, just going over, this is R and this is D and this is D prime. Okay, and there are a bunch of slice turns like S, C, and M. And another nice thing about this is that it's very easy to write down commutators. So for example, R comma U is the commutator of R and D. So what it does is, these things are already there. So let me remove all of this. So what this does is it does R followed by a U, followed by an R prime, followed by a U. So it's just convenient to write down instead of explicitly expanding things out and so on. And it also has an option of writing conjugates. So for example, if I want to say, so this is like saying you just compute A, B, A inverse. It's a slightly different thing than the conjugate we defined because we put the inverse in the beginning. But if you're willing to ignore that, then this basically is, so this is like you first do right, and then you do up, and then you do right inverse. Okay, so it's just convenient to do a bunch of things. Okay, so now let's do the following. Let's try to build our own commutator. Okay, since Varun has already had a chance to do this on Akadli, I want to ask somebody, can someone give me some sequence of moves that knocks off, let's say, this one corner?
Yes, so could do R prime dr.
So let's do R prime followed by a D, and then you do an R. Okay. This is one such example. Of course, some other nonsense is happening to the bottom two layers. I mean, some pieces are moving, etc. But we don't care about what happens here. Okay, so now let's. So can someone give me a move that only changes things in the top face? I mean, one trivial move is just up. Okay. Yeah, it changes things in the top face, but again, we don't care. So now let's try taking the commutator of these two things. Okay. And somehow magically, you end up getting some move that changed only 3 pieces in the entire cube. In fact, which these 3 pieces are also quite instructive. Okay, so let's not do the commutator because we have mentally told ourselves that the 2 moves we are going to be taking are this RD R prime and the move U. So what are the 3 pieces that can move? The only 3 pieces must be the common piece that is moved, which was this corner. The pre-image of the common piece under this move. Like you are basically asking what piece ended up coming at the end of all this. So that was this piece. This is some green, orange, yellow corner. So which was originally supposed to be here. Okay, so this is the common piece. And that corner happened to be the pre-image of the common piece against under move 1. The pre-image of the common piece under move 2 was that corner, because when we turned up, that was the piece that came to this common place. So the three pieces that end up moving are that corner, this corner, and this corner. Okay, so that's why, I mean, and in fact, that's exactly what happened. So, okay, so suppose, so here is a pop quiz. So suppose we do R prime D R like transverse distance. Okay, and let's say H was equal to U2. What are the three pieces that will end up moving?
So I mean this corner piece.
This corner piece.
The diagonally opposite piece on the top.
That piece and this piece.
This piece. Yeah.
Right. So if I now do R prime dr with U2, what you end up getting as expected is that other corner and these three things. Okay. So technically speaking, you can now use this to come up with your own local sequence of moves. Okay, that helps you solve the cube. Okay, so this is something that manipulates only the corners. It doesn't change the edges at all. It leaves the edges exactly where it is. And by edges, I mean these things that have two stickers. Okay, now we can ask ourselves, suppose I want to build, some commutator that cycles three edges. So what should we be doing? We basically tell ourselves, I want to come up with, okay, we'll just, like last time, one of the moves is going to be up. It only turns the up face. What I want to get is some way of knocking off, let's say, just this one edge. Like we just knocked off this one corner alone. Suppose we came up with our own move to knock off just this one edge. Okay, so what is one way to do that? So the simplest I can think of is the following. You use the middle layer to bring that thing down. Oh, sorry, then it's M, I guess. So what I'm doing is I'm just bringing this M down. And maybe I do a D, and then I do an M. So I just brought it down, knocked it away, brought it back up. And now if you take a commutator with U, once again, you will have three pieces that are moved. Because that was the piece that ended up coming to this place, and this is what up brought. So there are just three pieces there. Okay, so last pop quiz. This is just some, sorry, what happened? Oh, no, I should. Sorry, I'm just trying to figure out something. E maybe. Yeah, this is annoying. So maybe I should put an R instead of. Okay, so let's say this is my move G. Okay, and my H is going to be up. So I'm just going to write this down so that people see what is going to happen. So can someone tell me what the commutator of this G and H is going to be? So once again, let's ask, what is the common piece that is moved? That is this corner. So what's the pre-image of this common piece under, say, the up move? So that's going to be that corner. What's the pre-image of this common piece under the move that we are just doing? It's basically the piece itself. It's the same piece, right? It just happens to twist in its own place. I mean, what used to be here was the white, green, red corner. And at the end of it, you still have the white, green, red corner. It's just in a wrong orientation. So now if you look at the corollary, it said that the set of pieces moved was the union of 3 sets. 2 of the sets happen to be the same. So in this case, the union is just of size 2. Okay, so if you actually take the commutator of these 2 things, what you end up getting is only 2 pieces are changing, and both of them seem to be like, they twist in their own places. And similarly, just like this, you can come up with a way to twist the 2 edges or something. And these moves put together, you can basically solve them. Okay, it's painful, but what I want to show, since there's about 25 minutes left or something, I just want to come up with one systematic way of just using these to solve them. Okay, to make life easy, I'm going to work with a 2x2 cube instead of a 3x3 cube, just so that there are fewer pieces to move around. But, or in other words, let's just tell ourselves we are only going to solve the corners. We don't care about the edges. Okay, so let's write down our commutator. This is something that we were using. So what did Pranshu suggest? It's like r prime dr, right, along with u.
Yes.
Okay, so this was the commutator that was suggested. Okay, good. So now, to make life a little simple, okay, now let's start using conjugates. So far, we've only used commutators. Now I want to use conjugates. Right now, I have some 3 cycle that looks like what this piece went here, this piece went there, and that corner went here. That's the 3 cycle I end up having. Suppose I want a 3 cycle that basically just swaps it's a 3 cycle just on the top face. What do I need to do? So I hope the question is clear. Right now we have built some 3 cycle, which is this corner, and this corner. But this is a little annoying in the sense that they are on all different, they're not all on the same area, so that we can do this repeatedly. So suppose I want a 3 cycle that involves that corner, and this corner. Okay. So basically what I'm looking for is a way of relabeling these pieces so that I get what I want. So what do I want? I want to find some sigma such that that corner ends up going here. Once I do that, I can build my commutator. Okay, so let's just ask for the following. Let's come up with some sequence of moves whose job is to not change these 2. I don't want to change any of these 2 pieces. Okay, but I want to move the white face here to this location.
Yes, L2 works.
So L2 will move the white face, and so if I do L2, what will happen is the white face will end up going below. Suppose that's not what I want. I want the white. So basically, in this commutator, the thing that came on top was this orange color. Now, instead of this orange color, I want that white color to come here. So basically, just think of it this way. This sequence moved this orange sticker to this place. What I instead wanted to do is move this white sticker to this place. So what I'm interested in is moving this white sticker in place of this orange sticker. Okay. So there are other ways of doing it also. So one possibility, at least I can think of, is like, suppose I do L prime. What happens is, so that thing went below, and now let me bring it at this location. So I do a D. Okay, so that white sticker that used to be there now is here. So I hope that's okay. So we are just setting it up such that I didn't move these 2 corner pieces. I'm just moving this white piece to this piece. Okay, again, this was similar to problem 3 that I asked in the quiz. That is, keep 2 things where it were but move something else to some other point. This is just a slightly different operation. But now let's do the following. We had already built a commutator that had that did something. Okay. Now let's add this as a conjugate to that commutator. Okay. So I'm going to do LD prime as a set of moves, and then take its conjugate and take the commutator's conjugate with this. And you now automatically end up getting the 3 cycle that you wanted. Okay. All it does is it moves these three corner pieces in its own place. Okay. I hope that none of what we are doing right now is like super complicated. You can come up with your own sequence of moves, and you just need to put these things together in some systematic way. Okay. So far is everything. Sorry, Varun, go ahead.
Yeah. Add 2 after this. What happens?
Sorry,
Write it 2. Like I just want to. So this is a 3 size. So if you repeat this thrice, then basically we should just get the normal.
Yeah.
2, right?
So that's the second one, and this is the third one, and then you get the cube. Okay.
Yeah.
So yeah. By the way, if you want an actual sequence of moves, there is this button that's called expand, which will just expand this sequence of moves. It's some sequence like this. But at least it demystifies how you came up with this sequence. And again, this is something that you can come up on. Okay. So what I'm going to now do in the remaining time is like take some scramble that I just found online. And we're going to just solve this cube, but I'm going to do this for the 2x2 setting. Or we'll end up just solving just the corners alone. And that will tell you exactly at least one systematic way of just using these 3 cycles. Okay, so that's going to be in the remaining time. But before that, let me just move back to my iPad and okay, so I should stop share. Go back here. Okay. So let's just take, I'm just going to try out some example of this sort. Let's for the moment assume that you have a way of, just as a toy case. Let's imagine you have some puzzle where you're allowed to make these 2 moves. You can either swap location 1 and location 2, or you can do a cycle of all the pieces. Suppose this is all you're allowed to. In fact, let's modify this and say that, I'm just drawing it in a way which makes it easier for me to do the manipulation. Let's for the moment just say that you can only do the following. You can either swap these 2 locations, or you can turn this thing how many ever times you want. That's like saying you just have the permutation 2, 3, 4, 5. Okay, so I've just written down the current values of the stickers, and the smaller green things are basically to tell you what is supposed to be there in a completed state. What should have been there? Okay, so suppose all you have are these 2 moves. How do you systematically solve the cube, or rather solve this puzzle?
Wait, I'm a bit confused. What is this puzzle
So
right now?
let's say the puzzle is just the following. You're only allowed the following. You can either swap these 2, or you can rotate these 4 pieces.
Okay.
Let's say that's the only thing. In fact, I should have probably just written, this is just, let's say 2, 3, 4, and 5. These are the only 2 moves that are available to you. Okay, what is one systematic way to solve it? So the simplest thing I find is the following, which is right now I'm going to think of this as the transposition as a way of shooting this to the right place. And what I'm going to keep doing is bringing the right place to this location. Okay, so Okay, so I'll just show you I'll just demonstrate it and it should hopefully become clear. Okay, so what I'm going to do is the following. So at the moment, the thing on top is a 5. So I want to move the location 5 at the target situation. So I'm just going to do whatever this. Okay, and now let's swap these two. Okay, now I have 3 in this place. So now what I do is I again, what happened to that? I turn it so that location 3 comes here. Okay, and now I swap these two. Okay, so currently 1 is already solved in some sense. So let's start a new cycle. Let's just pick up some location that is not solved yet, like say 2. Okay, and then let's just rotate that to what happened. Okay, I mean, you know what I'm intending to do. What? Last attempt, if this doesn't, okay, I give up. So basically now what you'll do is you'll swap 1 and 2 by moving it there. And so this will become 2 and 1. And at this point I have a 2 here. So I will swap 2 with the location 2. So that will become 4 and 2 here. And then finally, I'll swap 4 with location 4. Okay, so that ends up making 1 and 4. Okay, so it's just one way of doing it. And in fact, what we are actually doing is the following. So what was the original cycle? It's like 1, 2, 3, 4, and 5, and it was this. So this is a cycle that looks like 1 goes to 5, 5 goes to 3, and 3 goes back to 1. And then 2 went to 4 and 4 went back to 2. So what we actually did was we just went through this cycle decomposition. We swapped 1 with 5. Then we ended up with 5 in our whatever buffer location. And then we swapped 5 with 3. And that's what we basically ended up doing. So we're going to do exactly the same thing with our Rubik's Cube. Okay, every once in a while, what is going to happen is we'll have a buffer location and we will move the right target sticker to that point, do our move, and move that target sticker back. It'll constantly be you conjugate, do the commutator, conjugate back. And that's what we're going to just keep repeatedly doing. It's obviously not the fastest way of solving the cube, but it's some way of solving the cube. Okay, except unfortunately we don't have a 2 cycle, we instead have a 3 cycle. And we need to figure out a way of using the 3 cycle instead of a 2 cycle. And I'm desperately hoping that this stupid twisting thing does not annoy me like last time. But let's just do the following. So again, let's say that the only things I'm allowed to do are rotate this, which is my 3 cycle. That's the 3 cycle that I know of. And there are these other pieces which can all be rotated if I want. Now I want to solve this permutation. Okay, we need to figure out how to solve it. So here is, I'm going to remove these gray things so that it becomes clear. So the first thing I'm going to do is put 2 in the right place. Okay, so, okay, let's hope this works. Yeah. Okay, thank you. And then let's take these 3 and we'll rotate. Okay, so in some sense, 2 has gone to the right place. Okay, it looks ugly. Okay, now here what we are going to do is the following. This is going to be our buffer location. That's the sticker I'm going to move to the right place every time. And what I'm going to do is I'm either going to move it this way or move it this way. I'm going to do one of these 2 things. So first, I see that 6 is in my buffer location. So I'm going to move the 6 sticker to this location. So I do this. I don't know why it just hates my. Okay, I'm going to do this. Now I'll swap these 3 things together. fine. I'm just going to just show you on the cube itself because it's just getting too painful. But hopefully that solve will make it clear. It's just damn annoying. There is the, okay. Is my screen visible? Not yet. Okay. Is my screen visible now? Okay. So, so what we are going to do is so let's keep it as a 3x3 thing, but let's just ignore the edges completely. Okay. So, or I don't know if it's just easier to, okay, let's keep it as 2x2. And since we need to figure out the right setup moves, I'm going to just keep this tab open just to test out setup moves. Okay. And we have our commutator. Where did we have that commutator? This is our, the commutator that we have. Okay. What it ends up doing is it moves that sticker here. This sticker goes here and this sticker goes there. Okay. And if I repeat this algorithm twice, then instead it is this sticker coming here, going there and going there, because it's like the cycle running twice. Okay, so this is what we have so far. Now the first thing I'm going to do is like this piece I'm going to end up solving. Okay, that corner, whatever that corner is. Okay, so let's ask ourselves, what is that corner supposed to be? It's supposed to be a red, blue, white corner. Okay, where is the red, blue, white corner here? It's in this location. Okay, so I want to move this corner up here. So one move that works is just B. I mean, all I'm doing is I'm just twisting that up. Okay, and now the game begins. Okay, what we are going to do is the following. We are going to look at this sticker. That sticker, I know a move that moves that sticker here. This is the 3 cycle that we have discovered. Okay, but that's not what we want to achieve. We instead want to move the sticker to its right place. So what I'm instead going to do is move the right place to this location. Then shoot the sticker and move this location back. And I'm just going to keep repeating this. That's it. Okay, so now let's look at what sticker is this. This is the orange, green, white. This is the orange, green, white piece with the orange facing top. Okay, so the orange, green, white is this guy. Okay, can you give me a way of moving this piece to this location without touching these two pieces? I hope you understand what I'm saying. So this is the correct target. I'm going to move it to my target, the target that I know of, run my move, and then I move it back. This is what I'm going to do. So what is a move that will bring this here?
Front.
Yes, front.
So just applying front is a possibility. Right? If I just apply front here, so what that piece ends up coming. So great. So that's the first thing I'm going to do. Where is this example solve? After this, so I'm going to do front as a conjugating operation and apply our awesome commutator to the conjugated expression. So let's just see what happened prior to that. This piece was not solved. Some other thing was there. But after we apply the sequence of moves, suddenly this piece is now solved. Okay. Okay, great. Now, but those two would have been swapped. So now I need to pay attention to this corner. Now I ask myself, what is this corner? This is the blue, red, yellow corner. Okay, now let's go ask ourselves, okay, where is the blue, red, yellow corner actually? Blue, red, yellow corner is like there. It's on the back face that's there. Now, how do I bring that blue, red, yellow corner to this location with the blue facing on top?
R prime.
No, but R prime will mess up the other two. I don't want to change those two things. Okay. I want to keep those two fixed, but otherwise I want to bring the blue corner. So it's often easy so suppose I do D prime first. So that
then,
brings the blue corner to this location. Now I can bring it up here by doing F. Right. So this is what we want. So now what we do is we do the commutator of this guy. I mean, conjugate this guy with this applied twice. Okay. So what ends up now happening is that that corner also got sorted. Okay. So in other word, sorry.
Can you just explain, like, how did you again figure out what was when you need to apply the
so in every step what is going to happen is the following. So forget the initial one move. Okay, think of it as like this corner will always remain solved throughout the rest of this thing. Okay, it's just that they will keep swapping among themselves. That's what will keep happening. Okay, whatever is the other corner that you have currently is what you're trying to solve at this step. Like we are just solving one piece at a time. We basically ask ourselves, where is this corner supposed to go? That corner is supposed to go here. So we came up with a sequence of moves that first moves this corner here. That is our conjugating sequence. That was what F was doing. And then we run our 3 cycles. Okay, so that ended up solving that corner.
Right.
Okay, now this is the corner that I now need to figure out where, I mean, it will just keep on alternating between these two. So now I need to know where is this supposed to go. That was supposed to go whatever here on the back. So I needed to come up with a sequence of moves that brings that back corner to this location. That is what D prime F prime did. Okay, now I don't want to move that corner here, but instead I want to move this here. So I have to repeat this algorithm twice because it's a 3 cycle. If I do it twice, it's the inverse, right? So that's why I repeated the algorithm twice. And at the end of this algorithm, that also goes. Okay, now we do the same thing. So now we basically ask ourselves, what is that corner? I mean, like, what is supposed to be in its place? And this is a situation where it's actually the correct corner, but it is just flipped in its own location. I mean, that corner is actually supposed to be the white, blue, orange corner, but it is just flipped in its own location. So let's imagine this is like starting a new cycle. Okay, let's just shoot it to some point which is not solved yet. I mean, I hope I had shown the other thing on the iPad properly, but notability just annoyed the crap. So what I'm now going to do is I'm just going to imagine shooting it here. I mean, I'm just going to shoot it to some unsolved corner at this point. Okay, so let's just shoot it to this unsolved corner. So at this point, that got shot here. Okay, so I'm needlessly going fast here. So currently, this is, think of the buffer location is going to keep changing between this corner, this corner, this corner, this corner. That's what is going to constantly keep happening. And one of the corners is always going to remain solved. In the other corner, we are constantly shooting it to the place that it's supposed to go to. Okay, so right now this corner is currently it's the same piece but somehow flipped in its location. So whenever a situation like that happens, just find some unsolved corner and move it to that unsolved corner. This corner was unsolved already, so I just moved it there because it's convenient. I don't need to do any conjugating business. So I moved it to this corner. Right now I have something else that I can play. That's the reason for doing this. Now, okay, now let's ask ourselves, this corner, where is this supposed to go? This is the orange, yellow, green corner. Where is it supposed to be? The orange, yellow, green is the bottom thingy.
Hey, can we just do one thing? Change this back to 3x3x3 because there the centers tell me what the actual colors are supposed to be.
Okay, so let's just go to 3x3x3. So the first thing we did was we just moved that corner to the right place. Now this is our buffer piece. This is where we know how to shoot. I mean, this is where we know how to shoot it to. So the first thing we did was we figured out where is this supposed to go? And it was supposed to go here. So we first did a conjugate with F so that that corner came here. And then we did our move. So at the end of it, that corner got solved. Okay. Now we asked, where is this corner supposed to go? The buffer will keep changing. It will keep changing between these two things. So now we asked, where is this corner supposed to go? So this was a blue, red, yellow corner, which is supposed to be, where is this supposed to be? It's here in this corner. It's on the back. So we wanted to bring that to this location. So we brought that to this location using D prime F prime, and then did the shoot, at the end of which that corner got solved. So far, so good. Now it just so happens that that corner, this is our current buffer right now. This is what we are trying to shoot currently, but it's the same piece. It's just rotated in its own place. Okay, so what I'm instead going to do is I'm just going to shoot it to some new place, some unsolved place. I just picked up this thing because I don't have to make any conjugate for it. Okay, and now let's again focus on this. What is this going to be? This is going to be an orange, yellow, green corner. The orange, yellow, green corner is actually supposed to be here. And I need to bring this piece here. Okay. There are plenty of ways of, can someone tell me how to do that? How to bring, okay, this also maybe not 4x4, 3x3. It's convenient to bring this orange. This is the sticker I want to bring here. Can someone give me a sequence of moves that does that? So one example is like R prime D R. So, I mean, this is just saying that we'll bring this down, move that in its place, and then bring that back up. Okay. So now let's take this as a conjugating operation and apply this twice. Yeah, and now that corner also got solved. So prior to this, it was like this, and at the end of it, that corner is solved. Okay. Now we again look at the next piece, which is like yellow, red, green. And yellow, red, green, we ask, okay, where is this supposed to be? The yellow, red, green is supposed to be here at the bottom. Let me just show you on the completed cube. This is where the yellow, red, green is supposed to be. This is the face I want to come. I want it to come here. Okay. So if I were to do F2, that stupid yellow, red, green thing comes to this corner. That's not what I want. So if you just do a D prime followed by F2, I mean these are, so the yellow, red, green ends up coming to the place that you want without affecting those two corners. So let's do that. And that ends up solving that corner also. So yeah, so basically I mean, it's not particularly insightful at this point, but the point is if you just keep, I'll share this full file with you so that you can, sorry, is this what I'm supposed to do? So what is the last thing that's left? So at this point, I should be shooting this particular thingy. And I'm just going to paste the rest of it. So I'll just show you one piece at a time so that becomes. So initially, we just started off with solving this one corner. And we said, this is the piece we want to solve next. We found the right commutator, sent it to that place. So that piece got solved. Then we said, okay, now this is the piece I want to solve next. We found the right commutator, sent it to that place. So that corner got solved. So if you basically look at what happens to this cube, like slowly one by one, the corners end up getting solved. Okay, so it's just one systematic way of using the 1-3 cycle that you have to completely solve the cube by just saying that, okay, this is the piece I want to solve, I'll move it to the right place. This is the piece I want to solve, I'll move it to the right place. So had you done this on a 2x2x2 cube, you would now have ended up with a completely solved cube. It's obviously nowhere close to the best way of solving it, because even for a 2x2x2, currently the algorithm seems to be taking 147 moves, which is clearly way more than the best possible sequence or something. But the goal here was not to find the shortest possible sequence of moves. The goal was to just find some systematic way of solving the cube. And this is just one example. And by the way, everything that I have said so far, there is a standard blindfold solve thing, which is called the old Boxman method. Okay, it's a basic method for solving a cube blind, which uses a slightly different algorithm. It doesn't use the 3 cycle that we are using. It uses a different algorithm, but the technique is the same. Okay, and I mean, you don't have to do this blindfold. I mean, like, it's just that you can keep staring at the cube and still execute the same sequence of operations. And it's just that this is one way in which I find all of these are moves that you can come up with on your own. Once you are a little comfortable with exactly moving pieces to the right place, etc. The rest of it is just you are constantly doing conjugates and commutators again and again and again. Okay, so I mean, these are things that if you try it yourself, that's the best way you can get more comfortable with it. I mean, otherwise this just seems like, I am pulling out these moves out of the hat, but technically none of these moves are like particularly complicated. Like if you play around with the cube just enough so that 2 pieces you are not allowed to move, but otherwise you can move pieces to its place. That's all you need for this for everything that we are doing here. Okay, so I'll share this, this particular scramble and this particular sequence of moves. I will add some comments to it to say exactly what the purpose of this was, so that it makes it easier for you to understand this entire sequence of moves. And hopefully you see that the only thing we used here was commutators and conjugates. And there's nothing special about a 2x2 cube or a 3x3 cube or a 4x4 cube or something. Once you know how to find the right conjugates, which also is mostly about come up with some sequence of moves such that in the top layer, it moves only one piece. And then you take a commutator with the up face, you automatically get one of those 3 cycles, which is basically all you want for these situations. And that will let you solve almost all permutation puzzles. There are some small parity situations you might end up with, which requires a bit more work, but at least it will tell you one systematic way to get very, very close to solving these puzzles. Okay, it's hard to just demonstrate it without, giving you too much. I mean, in a way that gives you a lot more insight. I would highly, highly recommend that you try out this example solve once I share this thing with comments, etc. So that you know precisely what is happening at every, in every step. And you're literally just solving one piece at a time. You don't care about what happens to the rest of the cube. You're just putting one piece at a time in place. Like it almost feels like, when one of the early times when you have a Rubik's cube at home and you get frustrated with the cube, you can't help but feel like taking it apart and putting them, in its place. And this gives you it gives you a legitimate but longer way of doing the same thing. It just tells you how to put one piece at a time. Okay, so this is all I wanted to say today. I'll share these things on Academy, or I'll put it on the Dropbox folder or something. And I'll highly recommend that you try it out. There are also supposed to be these apps for those, for topspin, etc. If you want to do the same thing for those other puzzles, Like there's something called topspin, there's something called Hungarian rings. If those are things you're interested in, I'll share that. I'll share apps for this, but hopefully the high level picture of what we were doing in each of the steps is clear. Okay, so let me stop here and just maybe pause for questions if there are any. So there is somebody, I mean, I have a guess as to who this is on YouTube chat, who seems to have answered something, or rather has a comment to add to Barun's thing, that biologist E.O. Wilson was called a racist for referring to the Gaussian distribution as the normal distribution. Whatever. Yeah. I think this is the same person that when we were talking about stabilizer said Brutus is in the stab of Caesar or something. Yeah. Okay, so let me stop here and maybe just take questions if there are any.
Okay, so is there a sequence of moves that swaps two pieces?
Good. I was hoping somebody will ask this. Turns out there is, and I leave this as an, I mean, that's an annoying exercise to figure out what do you do if this is what happens. I mean, if you end up with this, okay, I'm just writing down one sequence of moves. What it ends up doing is swap two pieces. Okay. And by the way, this works only for 2 cross 2 cubes or something. So if you actually see what it does to the 3 cross 3 cube, yeah, it swaps those two corners, but it also swaps two edges. Okay, so it does something else on the 3 cross 3 thing. So, I mean, this is the reason why I didn't, when I picked up this, whatever, this scramble and I tried this out, I mean, I'll confess that these are things that I had tried out yesterday itself, and it was meant to pick up a scramble and see what happens in the systematic solving that doesn't have this parity situation. But you're right; it might be the case that you end up with this whole thing, and then your cube looks like this. So, okay, so you need to now figure out how to solve, swap just those two corner pieces.
So if it's possible to swap two pieces and rotate just one piece in its position, then we could use that to solve the whole cube.
There's something very similar you can do here. So the point is, I mean, if you think about it, any commutator is an even permutation. Because anything that you're doing, you're also undoing. You're not doing it in the same order, but anything that you're doing is undoing. Whereas this particular thing is an odd permutation. So somehow if all you're using is commutators and its conjugates, etc., you'll never get an odd permutation. So the question is, we need to figure out, how do I fix this? Now, if only I had one more odd permutation that I could use. Now, turns out you always have an odd permutation, which is just the move up. Because up is a 4 cycle. And 4 cycle is an odd permutation. So basically, in a situation like this, what you do is you do up, and now you just fix the situation you are in currently. Yeah, so it's an annoying thing. I mean, like if you look up online, they will basically say, by the way, here is some sequence of moves that helps you in these parity situations or whatever. But if that's not what you want to do, if you want a more systematic way of doing it, this is one way.
Okay.
Yeah. Okay, so yeah, today's was probably a little heavy, but hopefully it's interesting enough that you can play around with it on your own, and I highly recommend it. It's a lot of fun when you see it for the first time, and even for people who have already who have some familiarity with speed solving, or some algorithms, which are the sequences of moves that does something very special or whatever. No, just look at that sequence of moves and see if inside it basically is a commutator or like a conjugate followed by a commutator or something. Because most moves are of that type. Like for example, even here you can notice that there is an RU, R prime, U prime, which is a commutator. And there'll be lots of them. For example, R prime, U prime, RU. That's another commutator. So there's certainly lots of these commutators generally hanging around. So it will help you demystify some of these things, some of these sequences of moves. Okay, so let me stop here. Some point today, I will just share the full solve with some comments so that you can try it out on your own. Okay, cool.